Okay. Okay, hello everybody. Welcome to my talk that is called Beyond the Frame, Using Computer Vision to Unlock the Potential of Video Data. Okay. How does this work? No? Oh. Okay. So, okay, well, this is a brief description of how the conference is going to be structured. So first I will do a little bit of a presentation, then I will do a brief introduction of computer vision, and then I will explain a real case scenario. So hello, my name is Paula. I'm an artificial intelligence engineer at Noumena. And to give some notes about my background, I studied audiovisual systems engineering at the University Pompeu Fabra in Barcelona, where I discovered that my passion is AI and image and video processing. So knowing that, I started working in a hospital in Barcelona where I did disease detection algorithms, that I work with images from patients with kidney transplants, that needed kidney transplants. And from the images, we were able to understand if the kidney was suitable or not for surgery. Then I started working as an AI engineer in Noumena. That is the place that I work now, and basically I develop computer vision algorithms. And a few notes about Noumena. Noumena is basically a company that its mission is to develop metrics and instruments to empower decision-making towards more efficient, resilient, and sustainable spatial solutions. Okay, so coming back to the topic of the conference, so what is computer vision? So for me, this is a very fascinating topic because, as we all know, like a video is just a set of images that is just like numerical values, RGB. So how come a computer is able to understand from that this is a person that has a tennis racket with a ball, and it's able to check the path of the ball and everything. So the answer to this is computer vision. So computer vision basically is a field of artificial intelligence and computer science that focuses on enabling machines to interpret and understand the visual content that is in the world that surrounds us. And so these algorithms analyze the visual contents, including shapes, colors, and motion in the images, and from this is able to extract features. These features are then used to train the algorithms to be able to, detect objects, motion, or even scenes. And with this, it uses machine learning techniques. Okay, so how is the workflow of a computer vision algorithm? So first of all, you have the data collection that is usually kind of tricky. Then you have the pre-processing, the development of the algorithm itself, and then the post-processing of the data. Okay, so the first step is data collection. And this is one of the most important and tricky aspects of all of these algorithms because you can have the best algorithm in the world, but if you don't have enough data or good data to train it, it will not work. So this is a key factor. And what do I mean when I say that it needs good data? So to have good data, you need large amounts, minimum like 100 images, like 100,000 images, for instance. Then you need a lot of variety of the data. Of course, if you have always the same data, it's just redundant and it will not add anything. You need the data set to be balanced. So in this case, I put an example of dogs and cats. So if, for instance, if you wanted to train an algorithm to be able to understand which is a dog and which is a cat, you need more or less the same amount of data. What else? You need the data, of course, to be representative. So if I input to the algorithm images of dogs that are just like dressed up like persons, it's not going to understand that this is a dog. And of course, you need the data to be labeled. So labeling means just that you need to tell that this is a dog and this is a cat, and just do this part. Okay. And the data collection is usually kind of expensive. Usually for a startup like that, this is a part that is very tricky, and you need a lot of personnel doing the labeling and recollecting the data. So a lot of the times what we do is that we use open source data sets, that in this case, the most common and the one that I'm more using is Coco dataset, which one in here I put like a lot of different open source data sets that are very useful. But personally, I'm most using Coco, and which has a lot of classes of objects and has nice labels, so you're able to train a lot of your algorithms with it. And then you can see the images of the Coco of the dataset itself, that you can see that they are nice images and they are very well labeled. Okay, now that we have the data collection, you go to the next step, which is data preprocessing. So basically preprocessing, well, first of all, you will make sure that the data is okay, so you check that all your data is good. And then you do the pre-processing because you want your algorithm to have the best data possible. You want to make your life easy, so you want the data to be nice. Normally, the first step will be to do some image pre-processing. So if you have videos that are kind of blurry, I don't know, if you want to do some enhancement, you do it in this first step, and you will apply this correction to all your images. And then, of course, you can also do some video pre-processing. So in this case, what happens a lot of the times is that you have videos that are recorded at higher frame rates, for instance, like 30 frames per second or 60. But normally, you don't need so much amount of frames, and also it makes your algorithms run slower because they need to process more data. So basically, a lot of the times you do some subsampling, and then, of course, you can do some rescaling depending on the definition that you need of the image. And you can do also some normalization. So all the video kind of have the same color, so it's able for the algorithm to understand the meaning of it. And once you have done all of this, of course, you encode the video, and then you're able to input in your algorithm. Now, for the part of the algorithms, this can be very extensive. So basically what I did here is that I put some algorithms that are like the most common use now in the industry, and that basically they are coming up every week with new ones. And then you can see here some images. So the first video is doing some pose estimation and tracking of the persons. That is very accurate, actually. This will be in the case if we wanted to do some disease detection. In here, you can see that there is also like semantic segmentation, but in this case, like there is the tracking, and then it's able to detect the whole body of the person. And well, here is the face detection and gender and age recognition. I don't know if you can read it, but it's actually very accurate, and it can detect very well the images. Well, and this is me. Okay. And now that you have the algorithm and you detail everything else, you can do the post-processing of the data. So basically, in this step, what you will do is that to check if the data has some redundancy, then you suppress it. You can do some thresholding, filter your data, and do all sorts of things. Then, of course, you can do like the extraction of the meaning of the data. That this depends on the algorithm that you implemented. So there are some algorithms that are the data that they are providing is already the one that you want. For instance, for object detection, if it says this is a cat, this is a cat. But when you do, for instance, pose estimation, it will give you the points of the human body, for instance. And from these points, you can interpret which is the pose of the person. So for instance, if the shoulders are doing in the same axis, you can see that the person is in front or behind. Okay. And of course, then you will also do some visualizations. So this is just for you to understand better the meaning and also to show to your clients. Okay, so now, this was the brief overview of computer vision. And vehicles and bicycles are interacting in the streets. And of course, the workflow that they follow is the one that I explained before. So, first of all, data collection. As I said before, this is always kind of a tricky part. So in this case, what we did is that we used separate data sets. One was for training, that we used an open source data set that was Coco. And then we used the prediction data that are the videos that we recorded from Barcelona. Okay, for the training dataset, what we did is that basically we used the Coco dataset explorer. In this case, it had all the classes that we wanted. In this case, it had all the classes that we wanted to detect, which were cars, motorcycles, bicycles, and trucks, well, and pedestrians. And from that, we downloaded the dataset. And this is what you can see inside of the dataset. So basically, you have your images and your annotations that have the same name. The file has the same name, so you're able to match them and train your algorithm. And of course, here you can see like the content of the annotations that basically it will say the position of the object, the content, like the ID of it, and the ID of the image. And with this, you're good to go. You can train your algorithms. For the prediction data. So here, basically, you can see a map that is from the streets of Barcelona. This is the neighborhood of l'Eixample. And in the green points is where we install the cameras. It was a total of number of 7 cameras, which contain an RGB sensor. We recorded 3 days that were Monday, Thursday, and Sunday, which basically we wanted to have like different days of the week to understand different movements. And then at the end of this record, we had 6,000 gigabytes of data stored. Well, here you can see some images of the process of installing the cameras and the content of the videos that you're able to see. Okay, so now we are going to the pre-processing of the data. So once we recorded all the data and had all the training data set, for the training data set, we did not do any pre-processing because we already work with this data set and we know that it's good for our algorithms. But in the case of the prediction data, we did some pre-processing. So the first step was to reduce the frame rate because we recorded at 30 frames per second, but when testing the algorithm, we saw that with 15 frames per second, it was the same accuracy. So we decided to lower all the frames per second. Then we did the correction of the distortion. I don't know if you're able to see it, but a lot of the cameras have a kind of a fisheye effect, which will distort the edges of the objects that are in the camera. This is not like very bad normally, so you're able to detect the object even though it has some distortion, but of course, it's good practice to have like a nice image that is flat and all the objects look what they are supposed to look like. In this case, we also implemented this that we say that they are corridors that are basically to help the algorithm to be more accurate. So in this case, what we did is that basically we painted in a way, we said that the parts of the street that you expect different classes. So for instance, in the pink part, you expect to have persons, in the blue part, you expect to have cars, and in the green part, you expect to have bicycles. And knowing this and providing this to the algorithm, you're helping it to have much higher accuracies. Okay, so the next step was the algorithm. So for this case, the algorithm that we created consisted on different parts. The first part was the tracking. So we used the YOLO 7 algorithm, which is very famous in the industry, and with the datasets, with the classes and datasets that we wanted. Then we also use a tracker. That a tracker is basically once you have your object detection class, it will detect an object for every frame. But you are also interested in know if the object is the same one from the frame that you have before. So in this way, you can mix these both algorithms and you can assign IDs to these objects. And from that, you will know how the person is moving. And then, of course, we did like some custom algorithms, so we're able to extract the data in the way that we want and implement a counter. Okay, so the structure of the algorithm was the following. First, you input the encoded videos. Then you run the object detection algorithm with the tracking algorithm inside it. And then what you do is that you extract the data from this detection. So in this case, for instance, this is a mock-up of a detection that you can have, that this is a car that has ID 001 at this time with this position. And with this, you can create a nice data set with all this data structure, and you're able to get some conclusions of this data. Okay, and now for the post-processing. So the post-processing was, first of all, of course, you always clean your data set, just because sometimes you like have doubles of something or I don't know, some redundant data. Then we created some visualizations that was just specific to our client, so he was able to understand all the data that was happening and in a way that is nice to look at it and just not numbers like this, because this is actually a screenshot of the data that you will get. So it's like the day, the time, the number of cars, persons, and bicycles that you will have at different times. And then we also did some ground truth comparison that I will explain a little bit more in the next slides. So these will be some of the visualizations that we did that is very just useful to understand some dynamics of the city. But here what I think it's not very, like you cannot see very correctly, but basically what we saw is that on Sundays there's a lot of people on the street, so all the numbers go very, very high on Sundays, whereas on Monday and Thursday, of course, you will not have so many people. Okay, and then for the ground truth comparison. So normally to know if your algorithm is working or not, you do some testing in the office and you see how it's performing. In this case, the client was very specific that he wanted to know how it is performing in this concrete data set in Barcelona. So what we had to do is that first we created the algorithm, we ran all the codes, and we have our outputs. And then we have to assign to someone in the office to do the human labeling. So basically, once we know the outputs of the computer, we also did the same process but with persons, so we know how accurate the computer can be, and then we compared both results. In this case, we got pretty good results, and you can see, well, the part that is more white is the part that the computer detected, and in the part that is like more gray is the human labeling. And here you can see that it goes very, very well. Of course, there's kind of an error, and also Barcelona is not an easy city. Well, I think most of the cities are not easy because there are a lot of objects. So if you have a camera and an object like overposes to another, you will not see the other object, so the counting is not as good as you could see. And then, of course, well, here you can see the accuracies, that also, as you can see, you don't get the same accuracy for all the classes that you are detecting. So, for instance, in this case, our model performed the best with persons, but the worst with bicycles. And basically this is because all the bicycles have a person in the bicycle. They are not like going alone. So sometimes if there was an object in front of it, it will detect the person, not the bicycle. So it will like mess up a little bit with the counting. But it was very, very good actually. Well, and this will be like the end of how this project went. I want to explain also some lesson learned. So this is me and my colleague from work that were very happy because we were already finishing this project. But in what the biggest lesson that we learned from this project is that you don't have to underestimate the timings, because these algorithms that take very, very long to run, like days, depending on your data, of course, but it's a long process. And we knew this, and for instance, if we needed 10 days to run all the codes, we said that we needed 15. And we did all the testing, and we were sure that we were gonna like have it on time. So we put all the codes running, and we didn't know why, but the code kept crashing. And we tried another time, and it kept crashing. So we did some investigation, and we saw that some of the videos were corrupted. Of course, the videos that we used for testing were perfectly fine, but apparently all of the rest were corrupted. So basically, we decorrupted all the videos, but just using FFmpeg. But the time to execute this was almost the same amount of time that we counted to run the algorithm itself. So, well, we had a deadline, so basically what we did is that we stole the computers from other people in the office, we installed all the software, and we set everything running, but it was very stressful. And now on, we make sure that we have a lot of time to run the algorithms. Then, we also saw that because Barcelona is a city with a lot of movement and a lot of trees, a lot of shadows, a lot of objects, it would have been better if we have like a bit of higher camera resolution, because a lot of the time with the shadows, you are not able to perceive correctly the object. So when you have a higher resolution, of course, you're able to kind of see better the object as humans. I mean, if you need glasses or not, you can see better the objects. But with this, you have to be careful, because if you increase a lot the resolutions, you increase a lot the timings of execution. So you need to compensate a little bit. Then the corridors, that is the thing that I explained you before, that is the way that we painted the streets, were implemented after doing some testing and seeing that the accuracy was not as good as we expected. And then we implemented this that didn't have any time of consumption, because it's just like depending on the coordinate, you're more likely to have one class or another. And this worked very fine. And finally, there was a problem that we realized after doing this project, that was the scalability of this. Because in this case, also because of the laws that are in Barcelona, we were not able to run the data, like all the videos, in a way that it was not in our offices. So basically what we did is that we installed the cameras, we recorded the video, we saved the videos in an SD card, and then these cards came to the office and we developed the algorithm around these videos. But what does it happen? That to run those algorithms, you need time and good hardware. So if we, for instance, in this case, we have 7 cameras and we had the hardware to run all of this, but if we want to do it in a lot of parts in Barcelona, maybe we need 50 cameras or 100 cameras. And and then it will mean that in terms of software and hardware, we will need much higher computation. So what we are implementing now is edge computing, which basically what we are doing is that we are creating cameras in our office that have a Raspberry inside of them, and they are able to run some part of the algorithm. And so basically, the part of the algorithm that we want to run in the camera is the object detection part. That is also the one that is very costly, because it has the entire image. And once you are able to extract the data of the objects, then you can do all the post-processing in the office, that at the end is just like a database with numbers and letters, which is very fast to run. And this is it. Okay, so thank you all for listening to my presentation, and if you have any questions, so please ask me.
Thank you very much.
You used YOLO for image segmentation. What did you use for the classification?
No, we did all the tracking with YOLO. In this case, it was YOLO 7, but we also tested with YOLO 5, which is very fast in comparison, but the accuracy was not as good.
Okay, but you didn't have to use your own models for classification later between bikes and cars and pedestrians?
No, we got the classes of it, and then we do the post-processing.
Yeah. Okay, I got it. And did you use any GPUs for this?
Yeah, the ones that with NVIDIA GPUs.
Okay, all right. Thank you.
Thank you very much. Well, I do have one question, being an application developer. Do you think this will still require a lot of resources for the foreseeable future? Like, if I wanted to build something consumer grade for this, I'd need a lot of GPUs and power. Is that going to change soon, or not for the moment.
I know that there are some companies that use cloud computing, but if you have to upload all the data to the server and then download it, I think it's very costly. So most of them just buy a lot of GPUs and then you run everything in-house.
So for now, just buy GPUs.
Yeah, for now, GPUs.
So no GPUs for gamers, sorry guys.
No, so I'm just wondering, what's a lot of GPUs? Like, what do you have in your office?
But depending on the project that you're getting. So like for this one, we needed to run with 3 computers. Well, it was, if we did it on time, which were like NVIDIA 3050, I think. But depends on how many images do you have and how like large are the videos. Depends on the project. You have to do some testing before.
That's actually reasonable. I was expecting like 10 H100s or something like that.
No.
Do you know why you had to reduce the frame rate?
Yeah, like
accuracy?
because for the tracking, depending on like how fast the object is moving, you will need more frames or less frames, but it'll walk so fast. So I mean, with 15 frames per second. What? Yeah, normally with 10, 15, we are good to go. Yeah.
So you mentioned the corridors that help you increase accuracy. What if you had like a moving camera? I'm expecting it would make things more difficult, but would it be still doable?
No, yeah, I think so it's doable, but to know the position of the person and everything, you want to know also the position of the camera. So now we are working with multiple cameras, so you're able to overlap the region, so you know the exact position of the person. But when you have it moving, all the objects are moving as well, so maybe like the tracker needs to be adjusted and as well as the position. Okay.
Well, thank you. Anybody else? Lots of questions today. Well, we got time, so.
So could you talk a little bit about the video capture and the quality of the videos and the compression that you did for the...
Okay, well, this part
Training.
I didn't do myself, but
Okay.
yeah, basically we have a team that was installing the cameras, and then I think the videos, I don't remember exactly the definition, but it was low definition. I think around 500 pixels or something like that. It was low.
Okay.
And then the frame rate was 30 frames per second. We had a lot of time of videos, like 3 days, like 24 hours. I don't know, any specific that you want to know?
No, just the format, for example, what codec did you use?
I think
for
they
Sony?
were M4B. If I'm-
MP4? MP4?
No, it was, I think, yeah,
It was Matroska, okay.
yeah,
Okay. Okay, interesting. Thank you.
okay.
Thank you very much. Well, again, thank you, Paula, for your great presentation.
Thank you.
And I think we have a coffee break coming up, right? My memory.